Okay, well, thank you, Maura, and thank you to the organizing committee for the invitation to present this talk. I have to confess that it's both a pleasure but especially a relief to be able to give this talk now, because we were not sure for quite a long time that DEEPWAVE was actually going to happen. It was first suggested to our aeronomy program managers at the CEDAR meeting near Logan, Utah in 2009. They said, go for it, it sounds like a good idea, but you have to be aware that you would be asking NSF programs that have never worked together in the past to work together, and if you succeed, it'll be the first time, and that would be great. So we had a lot of challenges along the way. The initial program was intended to go to the Southern Andes and the Antarctic Peninsula. That was, with a lot of effort by the NCAR flight crew, deemed not feasible. We had a big powwow with the NSF program managers and the NCAR folks, had all the PI team almost 2 years ago, and the judgment there was that we probably needed to cancel the program. But I raised my hand and said, wait a minute, I know there's some other place where we can go and make some of these measurements. And we said, we know you guys have been to Christchurch, New Zealand in the wintertime. You know you thought that was a good venue, so we suggest switching there. The science topics are much the same. And they said on the spot, okay, let's plan to try to do that. But that entailed another delay, a movement of the program, of course, a movement of all the ground-based coordination efforts, and a change in the venue, so another delay of another year. But the consequence was really good. We were able to get, ultimately, a really spectacular data set, I think. The NCAR and other supporting crews were very pleased to be in New Zealand. And I think the really big winners were the public relations people at NCAR, because they did not need to defend a program that put a large number of scientists on an island paradise for 6 weeks named Sangria. So I have many people that I'd like to thank. My PI team was really spectacular. So we had a very diverse team because we were trying to span large depths of the atmosphere. Ron Smith at Yale has a long history of doing mountain wave studies at lower altitudes. Mike Taylor, of course, you all know, and he does all kinds of wizardry with his imaging. Jim Doyle and Steve Eckerman have also a long history at the Naval Research Lab in mountain wave programs of different types in many places, and Steve Smith has very nice airglow imaging capabilities in both of the venues that we were considering. I also want to thank a very extensive additional team. We had co-Is with me at GATS and with Mike at Utah State, and the Germans, for example, with DLR, who joined us for half of the flight program, and many, many others that we need to acknowledge here. Overall, we had more than 100 people on the ground in New Zealand helping us with different aspects of this program. So it was a very big effort. We were all sleep deprived because we were forecasting every day and then flying every night. And so I had music in my head for days until after I got home from this program. So the region that we ultimately chose for this was, as I said, the South Island of New Zealand, as well as the surrounding Southern Ocean, the Tasman Sea, and Tasmania. The long range of the G5 allowed us to get access to all these regions, and we had flights that went up to Australia and out to the Eastern Ocean and well down into the Southern Ocean in addition. The thing that made it enticing is that this appears to be, based upon some of the satellite data, to be the second biggest hotspot in the Southern Hemisphere. We wanted to go to a region that hosted all of the, what we considered to be the major gravity wave sources at lower altitudes, especially topography, because all the hotspots seem to be ultimately strongly tied to topography. So we wanted to have particular sensitivity to those sources. And we had statistics of the lower level flow that suggested, based upon the previous mountain wave measurements that had made, that we would see a number of events that would be very enticing to us during our 6-week flight program. So another reason for going to the Southern Hemisphere, and I think perhaps the primary reason to be there rather than at more convenient northern latitudes, was the fact that we were operating in a latitude band that had a very nice propagation channel for mountain waves. We had sustained winds to the east that are necessary for vertical penetration by mountain waves to high altitudes. And we especially were in a hemisphere where sudden stratospheric warmings are very rare. We didn't want to have to change our science foci in the middle because all of a sudden the mesosphere was excluded from propagation because of a stratospheric warming. So we tried to make this as comprehensive a program as we could. We chose to perform measurements in a region that had all of the gravity wave sources represented. We wanted to expand the measurement capabilities of the GV in particular, and for that purpose, Mike Taylor and we at GATS developed 3 new instruments specifically for the aircraft that would extend its upper measurement capabilities from previously 18 kilometers up to more than 100 kilometers. So for the first time, we had an airborne platform that basically is as comprehensive as any of the ground-based facilities we now operate. And that was very exciting. We also wanted to expand this as much as possible and attract international participation, and for that purpose, we encouraged the DLR people to bring along their Flight Falcon, which was with us for the second half of the 6-week campaign that the G5 was in the air, and we had extensive support from a number of different modeling and forecasting groups that aided with the flight forecasting, and will be participating in our data analysis and hopefully model improvement and validation as well. So this is sort of a latitudinal cross-section from 40 to 60 south. We actually flew beyond these latitude intervals, but the horizontal bars here show the altitude capabilities of the instruments that were available on the DLR Falcon and the GV. The Falcon had a down-looking Doppler wind LiDAR that was able to measure vertical velocities and horizontal velocities by scanning. And the GV had, of course, its in situ microwave temperature profiler, all the in situ probes, and our new LiDARs that basically measured from essentially 20 kilometers up to 60, and then again from about 75 up to 105 kilometers. And Mike Taylor's AMTM aboard the plane and a second one on the ground spectacularly augmented these vertical profiling capabilities with the LiDARs. So this is Biff Williams, who built our LiDARs. He actually did a Herculean effort in squeezing 2 new, large, complex systems into 2 aircraft racks that shared a common telescope viewing out this ceiling port. We would have gotten an extra scale height out of the data had the larger telescope that had been promised to us for a long time had actually shown up in time to put it on the plane for the experiment. But nevertheless, we got what we considered to be really amazing data. Because there is such a small aerosol loading in the Southern Hemisphere compared to northern latitudes, we were able to extend the Rayleigh signals down to 20 kilometers in the Southern Hemisphere, and that is really unprecedented. We typically would not expect it to have been able to go below about 30 at northern latitudes. So we were able to get Rayleigh LiDAR temperatures essentially from 70 to 60 plus. The sodium layer measurements began typically down around 75 and extended up above 100. I only show it to 85 here. And so this is a plot for one of the cross-mountain flights, or two cross-mountain flight segments under conditions of relatively weak forcing that I'll talk about in greater detail a little bit later. And you see a large-scale wave that has a horizontal wavelength of about 240 kilometers, and it extends up, it refracts to larger scales as it enters a stronger jet and a larger mean wind in the upper stratosphere. And then there is this region where we have no data. And then the sodium LiDAR kicks in again and measures sodium densities in this region. And I've converted those, or Biff has converted those, to sodium mixing ratio here to show the excursions in the vertical of the displacements accompanying these waves. And what is really remarkable here is that this was an event that had fairly weak forcing, but it was able to grow and grow and grow throughout the atmosphere over many scale heights. And so in this region, it had a peak-to-peak excursion of parcels of 8 kilometers or more, which is we had never seen anywhere else. So Mike Taylor built, as I said, an AMTM, which is an airborne version of the systems that he now operates on the ground. This is a spatial keogram. Basically, it's in a long track plot of the cross-track field of view of that instrument along one flight segment across the South Island. And Mike also had the ingenious idea to add small additional IR wing cameras looking out each side of the plane and inclined up a little bit, so that he was able to image not just above the plane. This is the black and white version of this AMTM measurement aboard the plane. He was also able to look out both sides and extend the cross-track field of view up to 900 kilometers. So it's a remarkable capability that we can fly back and forth across the island and basically image the entire wave field over the South Island on every single flight. I need to mention this as well. He also brought to New Zealand and installed at Lauder, which is just in the lee of the Southern Alps, the AMTM that he's used at Alomar and at Bear Lake for some years. This has the same capabilities as the one that was airborne, but it has a larger field of view, and it allows in particular you to image the evolution of these motion fields in temperature at high altitudes for the first time. So we were supported by a very large number of ground-based instruments as well. We had balloons at several sites, Hokitika, Haast, and Lauder. We had imaging capabilities at Mount John and Lauder. Mike's AMTM was here, and the Germans brought a Rayleigh LiDAR that was also there. And so I've shown here the nominal flight, a couple of the nominal flight tracks east-west across Mount Cook, and sort of slanted in a direction that oftentimes was parallel to the incoming wind across Mount Aspiring. These were the two major mountain targets, and they ultimately led to a lot of the biggest responses we saw throughout the atmosphere. So I mentioned an extensive suite of modeling, and this was really remarkable. We had access to the ECMWF IFS model, which is a global forecasting system with 16-kilometer resolution. We had NCEP data. We had data from the UKMO. The Navy contributed forecasting and support modeling with their NavGem global model and their COAMPS local model. And then we had several versions of the Warf model run at several different resolutions by different groups. And then other models that were more specialized and will be contributing more to our analysis than to the forecasting. So basically, these participate in the forecasts, and we expect them to contribute to the reanalysis of the measurement environments. They will certainly aid in the interpretation of observations, as we're already discovering. We anticipate that they will be able to help us with assessments of model performance. In fact, some of the flights that I'll show exhibit surprisingly interesting agreement between the global model forecasts at relatively small scales and the observed structures that we saw in the stratosphere. And this was surprising even to the people who ran the models. So this is one example of a comparison between observations and modeling. This upper panel shows the downward looking Doppler LiDAR data in a vertical measurement mode. So these are true vertical velocities. They only penetrate down about 1.5 kilometers below flight level, because 1 over r squared comes back to bite you. And then they see additional responses at lower altitudes where they have sufficient aerosol loading at those lower altitudes. What is interesting is those measurements typically agree quite well with the larger scale wave environments that are predicted by the high resolution Warf capabilities at lower levels, but there are oftentimes trapped wave responses. These are ducted motions that are basically riding along the high stratification at the base of the stratosphere, and these oftentimes occur at scales that are too small to be captured by the 2-kilometer model, and so our German colleagues are now rerunning that Warf simulation with 600 meters in the hope that they'll be able to recover some of those structures as well. Well, this is a free-running Warf simulation that was performed by Ron's group at Yale. It was a 6-kilometer resolution. It began May 24th, about a week before our program actually began, the flight program, and it continued until the end of July. And it used European Center data as initialization, and it showed what it anticipated to be the potential for strong gravity wave forcing accompanying mountain wave dissipation depending upon what the background environment was like. So this first case, where we have relatively deep penetration, suggests that there was mountain wave breaking from around 15 kilometers all the way up to more like 35 kilometers. In another case, there was an event that had smaller amplitudes lower down but exhibited strong breaking here. During our field program, there were a number of cases where there was strong breaking that appeared to be confined to the lower and middle stratosphere, and this is what Ron refers to as a valve effect. It confines breaking to lower altitudes. And there was another case here where we saw nothing at lower altitudes, but strong responses much higher up. Another case in which the models did a good job of forecasting strong forcing at lower altitudes, but again, because of this weak stratospheric flow, there appeared to be strong breaking, and there was some hint in the model of secondary gravity waves radiating away from this region. This is the same region that is seen at the lower altitudes of the Rayleigh LiDAR sensitivity. And again, we see very similar structures here with some weak slanting structures. And then emerging out of the top of that are waves that are propagating both upstream and downstream and growing in amplitude and in vertical wavelength as they propagate to higher altitudes. So again, very nice agreement there. This was one of the more interesting examples from the EC perspective. We actually, on this flight, had the plane fly very far to the south to sample what the EC model had anticipated would be a large amplitude wave field in the stratosphere. And you can see that the agreement is not exact, but the contours here are the EC prediction of the field, and the colored map is our Rayleigh LiDAR temperatures. And you see a really remarkable comparison in many cases, and this suggests that the large-scale models do a very nice job of describing the larger scale wave responses for the sources that typically project onto those larger scales. The places where they fail are where they don't have the resolution to capture the smaller scale waves. So let me come back to RF-22 again. This was the very large excursion in the vertical. This wave was approaching a critical level, which the radar on Tasmania said was probably around 90 kilometers. So this had to undergo severe compression and dissipation. Below that level, we anticipate that strong braking may have occurred between 75 and 85 kilometers. And if you look at these other plots here, this one goes as high as 95 kilometers. This one goes as high as 105. These are all different realizations of the sodium mixing ratio, but with different color thresholds. You can see that coming out the top of this strong braking region with almost nothing seen at about 87 kilometers are small scale waves that grow to much larger amplitudes and exhibit both upstream and downstream propagation extending to much higher altitudes. So I think this is almost my last case. This is a case in which the forcing over New Zealand was quite weak, but there were stronger winds over Auckland Island, which is off to the south of South Island some distance. This island is about 50 kilometers across, but it's only 400 meters high, so it's a tiny, tiny obstacle. But the strong forcing there led to a ship wave pattern seen in Mike Taylor's images at 87 kilometers. This was the first time that kind of a response had ever been seen that high in the atmosphere. This shows the temperature perturbation from one snapshot with the AMTM aboard the aircraft of this portion of the wave field. And this is another case in which the forcing was relatively small at lower altitudes, so the wave was able to propagate more or less linearly, and so a linear Fourier array model was able to capture the scales and the amplitudes quite nicely in that response. And finally, this is the case that really caused us to recalibrate our assessment of what is a big event and what is a small event, because we had been operating since the beginning of the campaign with the assumption that people had made with previous mountain wave measurement programs where you were only measuring up to the flight altitude or higher. And in those cases, to get a big response at flight altitude, you needed a strong response at the source. So you needed typically strong surface winds. But this was a case on 21 June. Fortunately, it was early enough in our campaign to educate us. But this was a case where we looked at the forecast and we said, nah, this is a terribly boring event. There's not going to be anything happening. And then Mike comes in the next day and he shows us this movie, a movie of this event, and he says, look what you guys missed. So just to set the context, this is an image, an all-sky image from Steve Smith's camera at Mount John. You see some large-scale structures in the OH layer extending over the entire South Island and extending well upstream to the north and then off the shore to the southeast as well. This is a zoomed view of that field and the temperature at two different times in this red rectangle centered on Lauder where Mike had his AMTM. So I'm going to play a movie of that lasts a short time, and what you're going to see here is the evolution of a relatively transient mountain wave event. The mountain waves are identified because their phase structure is relatively stationary, so they're propagating upstream at exactly the velocity needed to compensate the incoming wind. And you can see very, very large amplitudes here. These are temperatures, so the blue is very cold, so it must be very high. The red is warm, so it must be very low. And the total temperature change here is on the order of 55 Kelvin. So this means that, again, there are extremely large vertical displacement in this motion field. And this happened at a time when we thought there was going to be no forcing. So I'll just list my summary statements here and answer any questions. Thank you.